Alright, so let's continue looking at sequences. I'm going to look at a different type of sequence today. All the ones we did last lesson were arithmetic, so there was a common difference that you add or subtract to go from one term to the next. We'll look at a different kind today called a geometric sequence. But that's just a warm-up here. I want you to try and find the general term for each of the following sequences. So if you look at the first one here, we have 7, 4, 1, negative 2. Hopefully this one looks a little bit familiar to you by now. You'll see that we're going down by 3. From one term to the next consistently. So this is an arithmetic sequence. Okay, and we know how to find the general term in this case. So we have Tn is a plus d times n minus 1. Okay, so in this case our first term is 7, our d is minus 3, so we have 7 minus 3 times n minus 1, and we do some algebra and we can simplify. So we wind up with negative 3n plus 10 as being our general term. Okay, so hopefully that one wasn't too bad, and hopefully went pretty quick after doing the homework from the last lesson. So looking at the next one though, you might run into a bit of a problem here. So if you look here, going from this term to this term, we're adding 3. Now we're adding 6. And now we're adding 12. This one is clearly not arithmetic. So yeah, so that kind of pattern won't work. Hopefully if you look at the pattern, you might be able to see something else instead. Instead of it being arithmetic and having a common difference, you might notice that as we go from one term to the next, we are multiplying. So 3 times 2 is 6, 6 times 2 is 12, and 12 times 2 is 24. So we can see our pattern here, and from here we could actually continue to generate the next however many terms we wanted to. We could go on forever if we wanted, but to find the general term, we haven't done anything like that yet. So let's take a look at what this one looks like on a graph. So here are the first 4 terms. Okay, so terms 1, 2, 3, and 4 are 3, 6, 12, and 24 respectively. And you can look at your last two terms, your next two terms here. 24 times 2 would give you 48, and 48 times 2 gives you 96. So taking a look at the graph here, if you graph those 6 points on a Cartesian plane, what kind of pattern do you notice here? And hopefully you can notice that it's clearly not linear. And the fact that we have a common ratio, that we're multiplying by 2 as you go from one term to the next, hopefully that screams out exponential to you. Okay, so this type of relationship with this type of sequence is going to be exponential. So how do we figure out the general term for something that's exponential? Well, let's take a look. So first of all, this type of sequence here where you have a common ratio, something that you multiply or divide by to go from one term to the next, that's going to be called a geometric sequence. Okay? And we generate that, and again, each term is generated by multiplying the previous term by some constant value called the common ratio. So in this particular example here, our common ratio was 2. We always generate the next term by multiplying the previous term by 2. So how do we find that ratio? Well, we can take any two consecutive terms, for example, the second term and the first term, and divide them to get that common ratio. And since it's a common ratio, that will be true for any pair of consecutive terms that you want. Okay, so as long as you have two consecutive terms, divide them, you get that common ratio. So some examples here, you have 1, 2, 4, and 8. Well, what's our common ratio? Well, 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. So that's our common ratio. Okay, let's take a look at the next one here. We have 12, 3, 0.75, 0.1875. So 3 divided by 12 is 1 over 4, or 0.25. Same thing for 0.75 divided by 3, and so on and so forth. So our common ratio there is 0.25, or as a fraction, it would be 1 over 4. Okay, so now in general, let's see if we can find a general term, much like we did with arithmetic sequences, because again, we want a formula to be able to generate the whatever term we want. So again, just like with arithmetic sequences, we're going to call our first term A. We're going to call our common ratio R. So our first term is just going to be A. Well, how do we get to the next term? Well, if our common ratio is R, we're going to multiply that A by R. So we wind up with A times R. And that pattern is going to continue. We're going to keep multiplying by R as we go from one term to the next. So A times R, so we have AR for term 2, times R, that will give me AR squared. Then times R is AR cubed, then AR to the 4th, AR to the 5, AR to the 6. And hopefully the relationship you see here is that the exponent on the R is 1 less than the term number. So in general, for our nth term, we'll have A times R to the exponent of n minus 1. So this right here is our equation for the general term. So Tn will be a, your starting value, times your common ratio to the exponent of n minus 1. So much like we had an equation for the general term of an arithmetic sequence, now we have one we can use for the geometric sequence as well. So let's take this and see if we can use that to get the general term for this guy on the first page. Okay, so over here, our first term was 3. We said our common ratio was 2. So our general term here is going to be 3 times 2 to the n minus 1. And there's our general term. Okay, so hopefully that's not too bad looking. Let's take a look at some more examples. So here's one I'd like you to find the general term for. Again, I'll let you try it on your own first. So start by trying to figure out what your a and your r are, and then try and put in the general term formula. Tn is a times r to the n minus 1 and see what you get. Okay, so in this case, you should see that the first term, the a, is 20. We can find our common ratio by taking any two consecutive terms and dividing them. So if I take the second term, 10, divided by the first term, 20, 10 over 20 is 1/2. Do the same thing with the third and second term. 5 divided by 10 is 1/2, or fourth and third term, 5 over 2 divided by 5 is also 1/2. So my r here is 1 over 2, or 0.5. So my general term, Tn, is a, which is 20, r, which is 1/2, and the exponent is n minus 1. So there's my general term. Okay. So let's move on. Let's look at this example here. So I'm going to give you a sequence here. I'll trust you to check if it's arithmetic or geometric. And once you find out what type of sequence it is, I'd like you to find the general term and then find what T12 is. So again, give this a try on your own first and push play and ready to go through it together. Alright, so just take a look at your answer here. I have my first term as 32 over 243. To find my r, again, like the last example, I take two consecutive terms and divide them. So if I take the second term, 16 over 81, divided by 32 over 243, when I work out that division of fractions there, I get 3 over 2 for my ratio. I should confirm that this sequence is in fact geometric. I didn't actually say it was. So I did the third term divided by the second term, got the same thing. And I would get the same thing if I took 4 over 9 divided by 8 over 27. So every pair of consecutive terms I have there creates the same common ratio, so I know it's geometric. And I know my r is going to be 3 over 2. So from there I can create my general term. So remember, Tn is a times r to the n minus 1. So I put in my a of 32 over 243. I put in my r of 3 over 2. And once I have that equation, remember I'm trying to find T12. So I put in 12 for n. So I wind up with 3 over 2 to the exponent 11. And then once I simplify that in my calculator, remember this 3 over 2 to the 11 is 3 to the 11 over 2 to the 11. And I wind up with 729 over 64. And again, it was only T12, so once I found out my r, I could have just continued multiplying everything by 3 over 2 until I got my answer. But that takes a long time. And again, if it was a larger term number I was asking you for, like T38 or something like that, it would take you a lot longer. So finding the general term is the way to go here, because once you have that, you can just sub in whatever term number you want and get the term. Okay, so with that in mind, now I'm going to give you another sequence here, and hopefully you see it's 7, 14, 28. You can see there's a common ratio there of 2. Okay, and an a value of 7, our first term. And I want to know which term has a value of 469,762,048. So again, first thing I'm going to do, before I even worry about this ugly number over here, is find the general term. So my a is 7, and my r is 2, so I have 7 times 2 to the n minus 1. Now, we did something like this when we looked at arithmetic sequences. I'm being told that there's some term out there, I don't know it, but some term that's going to be equal to that ugly 469,762,048 number, and I want to know which term makes that happen. So there's going to be some n value, some term number that's going to make the term equal to that. So I'm going to set Tn equals that 469 million. And I got to figure out what value of n makes this equation actually work. So see that with this geometric general term here, my unknown is in the exponents. I have to solve an exponential equation to make this happen. Now, if you're a little bit rusty on those, remember that to solve an exponential equation, you need to put both sides of the equation under a single power with the same base. So I don't have a single power right now on the right side. I have a 2 to the n minus 1, but that 7 is in the way. So the first thing I'm going to do is divide both sides of the equation by 7. Okay, so the right side of my equation is now 2 to the n minus 1. And the left side is now, once I do that division, $67,108,864. So I need to put both of these under the same, under a single power with the same base. So my base on the right side is 2. So I'm going to try and express the number on the left as a power with base 2. Now, this is a very, very large number, and I don't necessarily expect you to recognize that that number is a power of 2, but since it's a grade 11, the only way we can potentially solve this at all is if you can have both sides of the equation under a single power. So that tells you that somehow this number has to be a power of 2. So you can use some trial and error in your calculator. Try different exponents of 2, and you'll eventually narrow in on that. So 2 to the exponent of 26 will eventually work, and again, it'll take some trial and error. Don't expect you to just recognize that this is equal to this, but you try a couple in your calculator, you'll narrow in on the answer after a couple tries. So once you have this being the case, you can now equate the exponents. So 26 is equal to n minus 1, which means that n equals 27. So that means the 27th term of this sequence is 469,762,048. Okay. So again, it's the same types of questions we saw with arithmetic sequences, but solving them can take a little bit of a different approach, obviously, because now we're dealing with exponential equations versus linear equations. Okay, so again, another type of question we saw back in arithmetic sequences. I'm giving you two terms in the sequence. I'd like you to find the general term, and once you find the general term, let's find the first three terms in the sequence. So what I'm going to start with here is, again, if I want to find my general term, Tn is a times r to the n minus 1. And all I know right here is, well, is nothing. I know T16 is this and T5 is this, but I don't know anything about a and r. So what I'm going to use is the fact that T16 will be equal to a times r n minus 1. If n is 16, it'll be a times r to the 15. Okay, and I'm also going to use the fact that that means that T5 is a times r to the 4th power. Okay, and if I use the fact that I know what these terms are equal to, so that means that I'm going to have T16, which is 71,744,535. That's going to be a times r to the 15. And if T5 is negative 405, that means I have minus 405 being ar to the 4. Okay, so again, what I see here is that I also have two equations, two unknowns. Okay, now, looks a little bit different from some other situations with two equations, two unknowns. All those have been linear so far, but these ones, you have exponents in there, so solving is a little bit trickier. Okay, let's talk about how we can solve that. So the whole idea of substitution can still apply here. I mean, I can still try and use one of these equations to isolate for a variable. I'm going to choose to work with this one here because the numbers are smaller. So if I have negative 405 equals a times r to the 4th power, I can isolate for a if I divide both sides here by r to the 4. That would mean that a is equal to negative 405 over r to the exponent 4. Okay, once I have that, I can replace it in the other equation, and let's see if it actually simplifies anything for me. Again, I'm using substitution here, so hopefully this will get rid of one of the variables. So I have 71,744,535. I've replaced a with negative 405 over r squared. Sorry, not r squared, r to the 4th. And that's going to be times r to the 15. So again, with this equation here, there's no longer any a's, it's just r's. And hopefully I should be able to solve this now for r. So we'll do that in part 2 of the lesson.